Yeah.
Ladies and gentlemen, my name is Petr Kluson, and I'm Scientific Vice President of the European Federation of Chemical Engineering. And I'm very, very pleased and happy that you join us for a common afternoon today, which will be devoted to very exciting topics which are associated with activities of the Working Party on Loss Prevention, which is chaired by Professor Bruno Fabiano. Bruno is here. And so he is the main organizer of this spotlight talk, and Bruno will tell us in a few minutes what the seminar is going to be. Okay, what the webinar is going to be about. It will be about safety and risk of energy transition. So we will hear more about it. We will have this afternoon 4 lectures and potentially the panel discussion afterwards. I'm also very glad that Professor Martin Pu, who is the head of the Scientific Secretariat of EFCE, is here, and all the speakers. Maybe now, Martin, I'd like to ask you for a very short presentation, which is dedicated or devoted to something different than which is covered by the program this afternoon. As you may know, European Federation of Chemical Engineering is organizes many events throughout the year. In the next year, we will have the Congress in Berlin in September, but very soon in Paris, December the 5th, there will be a very, very nice event, which I'd like to invite you for within the European Forum on New Technologies, which is annually organized by EFCE. We are actually opening activities of a completely new section of EFCE, which is called Chemical Engineering as Applied to Medicine. And I'm sure that also for your scopes, there might be quite a lot of interesting lectures and interesting people to be met. We still have few openings there, few empty spaces for registration. So check the web pages of the European Federation. And if you are interested, join us in Paris as well. Right, so that's all from me at the moment. I'm of course staying, and I'm looking forward to a lot for the lectures. And Bruno, now it is your turn, and tell us more about the program for this afternoon. And thank you a lot once more for organizing this spotlight talk within the umbrella of the EFCE. Thanks a lot.
Thank you, Peter, for your kind introduction. I am sharing my screen now.
Yeah. Join meeting.
So, my name is Bruno Fabiano from the Department of Civil, Chemical and Environmental Engineering of the University of Genoa in Italy, and I'm currently the chairman of the Loss Prevention Working Party of the European Federation of Chemical Engineering. I welcome all the participants here to this webinar, which is within the framework of the new series of the Spotlight Talk series, covering hot and significant topics of the chemical engineering. My task in this introduction is the simple presentation of the speakers. Nevertheless, I see that we have a rather large number of registered people, both young and experienced. So let me spend just a few words of introduction for all. But first of all, I want to express also from my side, my deep gratitude to EFCE for the webinar organization, and to Martin Pu for her always effective and precious activity. Coming to the Loss Prevention Working Party, it was founded in 1971 during a symposium in Newcastle upon Tyne, UK, and it covers all aspects of loss prevention and safety promotion with people from academia, industry, regulatory bodies, also from outside Europe in the last time. The mission of the Working Party is to foster the exchange of knowledge, experience, and ideas in the field of hazards linked to processing industries, of loss prevention in chemical processes, in process and plant safety. And by doing so, the state of the art in the community dealing with these topics shall be broadly available, minimizing those losses linked to not considering already available know-how. Additionally, this mission will contribute to develop and improve the state of the art, shaping the loss prevention practices of the future. And This is just one of the aim of this webinar. Here you can see that how 50 years of loss prevention and safety promotion in the process industry are outlined by the history of the main event that the Working Party organizes every 3 years, and which is the Loss Prevention Symposium. And here you can see the different hosting countries within the European continent from the origin to nowadays. And the symposium nowadays more than ever aims to be broad in its scope and to bring all process safety aspects together. And indeed, our symposium contributed to advance knowledge and awareness in all fields of safety and loss prevention, and let me say, to raise and expand the safety culture, which is necessary to face present problems and challenges. I invite you to visit the Loss Prevention Working Party websites, where you can find under the section History the content or the full paper of all the loss prevention symposia, starting from the very first one. Here you can note the link to the Loss Prevention Working Party and to the EFCE websites, both having a lot of information. So this webinar with leading experts focuses on safety and energy transition. Why? Well, first of all, energy is the engine that underpins an economy, and we are going towards an unprecedented energy transformation. This topic represents an emerging facet of the safety and loss prevention domain. And at the last Praga Symposium, which was in June 2022, was very appealing for delegates as a new challenges in our rapidly evolving risking world. In fact, we all know that we have to face new challenges, and indeed we are in the time of a sort of perfect storm where 3 drivers play a determining role, namely digitalization, climate change, and energy transition. They provide significant opportunities to enhance process safety, but equally they require to managing the connected risks. And the last years introduced 2 additional catalyst factors, the COVID pandemic and the Ukraine crisis, which sent shock waves through the sector and are likely to influence how we organize and manage our plants and business to be more resilient and support the deep decarbonization of the global energy system. Now we can move to our webinar, and here you can see the program of this workshop, which collects worldwide international experts from academia, industry, and institution in the spirit of our loss prevention symposium of the Working Party. We shall have a single session, and each delegate will present a topic, and here you have an outline, and after each speech, we shall have a question and answers slot. The lectures will focus on key issues in the energy transition area, hopefully enabling attendees to sample novel ideas and encourage cross-fertilization between specialist areas, because actually energy is a socio-technical system. Coming to the program, you see that the first speaker is Maurizio Rigolio from Tecnimont, Milan, Italy. He will deal about process safety challenges related to energy transition. The second speaker will be Tjis Koerts from European Process Safety Center. He will report about the new hazard related to the energy transition. Then we shall have Professor Valerio Cozzani from University of Bologna, who will report about risk management and trade-off within the energy transition framework. And at last, we shall have 2 speakers from the Mary Kay O'Connor Process Safety Center, Texas, who will report about process industry safety challenges by new energy carriers, materials, and new process types. At last, we have a sort of round table to, if there are some further questions to be analyzed. I remember that you can ask after each presentation your question by using Q&A, and then following the order, you will be unmuted to make your question. So I give immediately the floor to the first speaker, who is Dr. Maurizio Rigolio. He is currently the head of the Department of 40 persons in his organization, and he is responsible for the correct implementation of HSE and loss prevention requirements during the design phase of the EPSC projects. He is also leading specialized groups on noise control design, environmental engineering, and permitting and authority engineering. He is a professional HAZID, HAZOP, and SEAL chairman, and he led several process hazard analysis and pre-startup safety review in different international projects. He is member of the European Process Safety Congress and of the Italian Electrotechnical Committee for Hazardous Area Classification. He will report about process safety challenges related to energy transition. So the floor is yours, Maurizio.
Thank you, Bruno, for this very, very kind presentation. I am very honored to be here to speak about the process safety challenges related to energy transition, which is one of the very important fields in which everybody nowadays is speaking about. I'm trying to share my screen to start with our presentation. And again, I am Maurizio Rigolio. I am the responsible of design HSE department in Tecnimont. That is a company belonging to Tecnimont Group. That is an Italian multinational company in the sector of EPC contracting. In the presentation of today, I will discuss about the process safety hazard to some energy transition sectors, in particular with focus on some three aspects related to hydrogen carrier, to the mechanical recycling, and to the bio-based solutions. But it's important also to understand why this process safety hazard could be critical in this field, because there are hazards that are introduced in a new context. What is the purpose of energy transition? The purpose of energy transition is basically to reduce the impact on the environment, to create new products for renewable feedstocks, and to enter new markets with a non-fossil footprint in order to give a contribution to a sustainable development. It's in practical is to move the energy triangle towards the environmental sustainability without forgetting the security and necessity and the economic development and growth, which are part of the triangle of energy. Why the energy transition is necessary? It's necessary to mitigate the climate change effect and to reduce the greenhouse gases emission. As an overview of this graphic of the APA, the greenhouse gases emission are basically for almost 80% generated by carbon dioxide, and in a few cases by methane, nitrous oxide, and fluorinated gas. And as a source of European environmental energy, the most challenging of CO2 emission are related to energy and transport.
Maurizio, sorry.
Yes, please.
The slides are stopped.
The slides are not running.
Yeah.
Okay, so
Sorry.
maybe I have to move from. I have to proceed in this way without the slideshow, because the slideshow is not giving effect. Now, are you seeing my slides?
Yes.
Okay, so I will proceed in that way. Sorry. Okay, we are discussing regarding the energy triangle, and now we move to understanding what are the sources of CO2 emissions that are basically generated by energy and transport, and in some case by industrial process and agriculture. But the main issue of greenhouse gases emission, CO2 emission in particular, are related to energy and transport. So there is a need to move to make a sort of energy transition in order to move from the current use of energy through fossil fuels to other possible renewable sources of energy. This is the way in which NESCAM, which is a company belonging to the Tecnimont Group, is interpreting the energy transition requirement in a sort of pyramid, splitting the energy transition in three sectors: the green, the circular economy, and the so-called green in the brown. For greening the brown is intended to optimize the use of energy with energy efficiency, with decarbonization, with carbon footprint reduction, and to use renewable energy and new energy carrier, like, for example, the hydrogen that from renewable sources. The circular economy basically is related to mechanical recycling and waste to chemical plants. In the figures that are related to products that are generated by a plant of Tecnimont subsidiary Maurizio, which is completely making use of mechanical recycle in order to produce new bioplastic products. And the third sector, which is the green, is related to the use of the production of fuels, polymers, chemicals, fertilizers, and coatings related to the starting from bio-based products. These are how our group is interpreting the energy transition approach. But what is the criticality? What can be the criticality with respect to new hazards generated from the energy transition? The common perception is that greener is equal to safer, but this is not always true, because it is correct that the high hazard that is related to the management of fossil fuels in several cases could be reduced, but at the same time, flammable fluids could be still present in several energy transition sectors, and in some cases, there is also the introduction of new sources of hazard. Here is a list of the main process safety hazard related to various sectors of energy transition. Hydrogen, for example, is causing potential hazard like jet fire and blast. Mechanical recycling is can generate fire, and in case there are the handling of dust can generate also dust explosion. The bio-based products at the end are producing products which can be flammable. So the risk of fire due to flammable fluids is realistic. In case of LNG, there could be the chances of having blast, fire, and BLEVE. For CO2, there is the possibility to have pneumatic blast and intoxication in carbon capture plants. Also, renewable energy, as we can see in the picture of on the right side, can cause some drop-it-off hazard and also in some cases also some fire. Thermal runaway, fire, and blast are potential hazard generated by the handling of batteries. In the right side at the bottom, there is a picture of a big battery fire, a big battery charger station fire in India. And also from where the handling of waste, some toxic and noisy release and several fire can be generated. So we don't have to underestimate this potential hazard also from energy transition sector. In my presentation, I would like to go in detail of 3 potential cases of hazards related to the hydrogen, related to the mechanical recycling, and related to the handling of bio-based products. Let's start from hydrogen. Hydrogen is the simplest chemical element. It's generated by 1 proton and 1 electron. And the most common form of hydrogen, stable with a neutral charge, is H2. It is gaseous at ambient condition. It is liquid if stored at minus 250 degrees at a pressure from 3 to 8 bar. Hydrogen is the most abundant chemical on Earth, but very little exists in pure state. The majority of hydrogen is water and is in water as H2O. Hydrogen is one of the pillars of energy transition, but we cannot consider hydrogen as a new substance. It was discovered many years ago, and it was used already from the 50s as rocket fuel, as catalyst for desulfurization of hydrocarbon. It was used combined with nitrogen to produce ammonia in the steam reforming and in the green ammonia and in the standard ammonia plants. And it was used as town gas in the UK, in France, and USA up to the 50s. And then it was phased out because the natural gas was cheaper and cleaner. But let's say we can consider that hydrogen now is becoming new for its possibility of being used as carrier of energy. but it was used in industrial plants since several years. I would say several decades. What are the properties of hydrogen? The hydrogen has a very, very small molar mass because it's just constituted by two atoms. It has a very, very low flash point, minus 25.3 degrees, and a very high autoignition temperature. But the risk, the main hazard of hydrogen is due to the fact that its flammable limits are very wide, starting from the 4% of LPL up to the 75% of UFL. And another criticality of hydrogen is the minimum ignition energy, which is very, very low. On the other hand, it could be positive, the fact that it is 14 times lighter than air. So when released in the atmosphere, it goes towards the sky very, very quickly. Comparing with other hydrocarbons and flammable fluids, hydrogen has therefore a very low ignition energy, a very high volatility, and a high autoignition temperature. So summarizing what can be the good news of hydrogen is a non-toxic substance and is non-noxious for the atmosphere. It is not polluting for the liquids, and it generates no solid waste. It's a light gas. That means that in open and ventilated area, it disperses very rapidly. It burns quickly with a flame which has low radiant, but on the other hand, the flame is invisible and has a high temperature. In outdoor open area, has a low risk of explosion. On the other side, what are the bad news? It is odorless and colorless, so means that it's undetectable by the human sense. It's very easy to ignite, as we told before, due to the large inflammability domain and the very low ignition energy. There are a lot of potential ignition sources like static electricity, metal fracture, friction, vehicle exhaust. The explosion in closed and congested environment might have very heavy consequence because it could be generated the phenomenon of transition from deflagration to detonation. It is highly reactive. The combustion releases much more energy than other gases, and in case of confined space, it can generate very important overpressure. It leaks very easily due to tiny molecular structure, and for this reason, it can cause embrittlement. The typical scenario, typical process safety hazard related to the ignition of hydrogen is the jet fire. The flame is emitting predominantly radiation in the UV region and very few in the visible region. So it means that hydrogen flames are difficultly visible in the daylight. And the burning velocity is very, very high, 8 times higher than other hydrocarbons. This high burning velocity can increase the frequency of the transition from deflagration to detonation. The explosion of hydrogen is an explosion that starts in some case with deflagration, that means lower than the speed of sound, with a probability velocity less than 100 meters per second, and with a very low overpressure. In case of transition to detonation, the subsonic flame can accelerate and can become supersonic. It occurs most often when the turbulence of planes and when the fire explosion scenario is partially confined and obstructed. In this case, the deflagration transfer to a detonation, which means supersonic exothermic fronts at more than 10 meters per second, up to 2000 meters per second, and with a very significant overpressure, up to 20 bar G, therefore with some catastrophic damage. Apart from fire and explosion, the third very critical process safety hazard for hydrogen is the embrittlement. Embrittlement is the penetration of hydrogen inside the crystalline structure of the materials. It can be classified basically in two categories. The real embrittlement, which is called HEC, embrittlement cracking, which is a degradation with time of the mechanical properties due to permeation of hydrogen inside the materials, and the HTHA, which is the high temperature hydrogen attack. That means that when hydrogen is handled at high temperature, the hydrogen can dissolve inside the steel, and the reaction with the dissolvent carbon can form methane, causing fissures and cracking. So, from process design point of view, what are the most critical scenarios that can be considered while designing a hydrogen plant? First of all, it is recommended to avoid a closed environments, because due to the hydrogen volatility and accumulation on the environment ceiling, the closed room has a significant risk of fire and explosion. And so when feasible, the closed room should be replaced with shelter structure with the maximum possible provision of openings towards the top in order to let hydrogen dissolve in the atmosphere. Another process safety designed to be taken into account is the material selection. Caused due to the embrittlement, the selection of the material shall be investigated with very specific cares and with consideration about the pressures and the cyclic condition that has to be taken into account. At low pressure, it has been demonstrated that some plastic material, I would say some non-metal material like GRP and FRP, are much less sensitive to embrittlement than steels, which has or for which the only material considered suitable for hydrogen is the stainless steel. Of course, if the pressure increase, the non-plastic material cannot be used because the non-metal material cannot be used because they cannot withstand high pressure. Other process safety design aspects to be taken into account are the fugitive emission, because this hazard is very significant due to the hydrogen nature. Therefore, a specific selection of equipment, seals, and piping fittings has to be applied in a so-called hydrogen service. And also for what considering the refilling stations, the loading station, a particular attention to the use of coupling of H2 with specific tightness in order to minimize hydrogen leakage shall be taken into account. So concluding the aspects related to hydrogen, it is a substance that has some criticalities from a hazardousness point of view, but if the design is proper and accurate, the risk of fire and explosion from hydrogen can be in a certain way minimized. Moving to a second topic of this example of process safety hazard, we move to the mechanical recycling plant. Mechanical recycling plant seems at a glance much less hazardous than other kind of plants. This can be true. These are plants in which, starting from recycled solid, plastic material are treated, purified, extruded, and compounded and packed in order to be ready for the reselling. The feedstock are plastic solid waste, in some cases municipal waste also, or polyolefins industrial scratches. According to the composition of the feedstock, the purification section can be quite different. The process of the mechanical recycling is starting from the waste collection up to collection in a material recycling facility, separation, compacting and baling, crushing, washing, melting, extruding, pelletization, and processing of new products. Starting from the collection in a material recycling facility up to the pelletization is the so-called recycling process that is generated in a single facility. What are the hazardous sources of a mechanical recycling plant? First of all, combustible dust that are in some cases related to plastic particles with granulometry less than 25 micron. But in this case can be also some dusty additives that are added to the pelletizing in order to increase the properties of the plastic recycled material. There could be also some waste in a plastic plastic mechanical recycling plant. There are some battery room, forklifts, vehicle recharging station, combustible oil, grease, and peroxide. So some hazardous substances are present. The main hazardous scenario is generated from the dust, basically. In particular, in case of close congested environmental with some potential initial sources which are part of the process itself, like rotating components, electrostatic charge, friction, and high temperature in some case, a dust explosion can be generated. Dust and waste fires can also generate high fire loads because in this kind of plants there are very huge storage area, And from flammable combustible fluids and batteries, fire can be generation. If peroxide is used as additive, also the composition of peroxide shall be taken into account. In this picture, there are two examples of plastic recycling facility fire. As you can see, the fire can be very huge, because if the fire happens in a congested area, it can all the 5 elements of the pentagon dust explosion can be present, because if there is oxygen, ignition, and dispersion of dust particles, presence of dust, if the dust cloud is confined, an explosion could be generated. In order to assess the dust fire and explosion scenario, the following properties shall be taken into account: the granulometry, the minimum ignition energy and the minimum ignition temperature of the dust cloud, the self-ignition temperature of a layer, the minimum explosive concentration, the maximum pressure of dust explosion, and the explosion constant, which is a function of maximum pressure and time, which is typical of each dust. The problem is that these kind of properties are not easy to determine, and can be determined only with some test specific for the kind of dust, especially in case of plastic recycled plants, because the dust, the treated dust are really a mixture of different kind of raw materials. And so the only way to find this kind of properties is to make some particular and specific tests. The profile of a dust deflagration is a very wide increase of pressure up to a certain period of time, generating a level which is called Pmax, maximum pressure at that time. And in this case, after that, the pressure is slightly decreasing. The specific constant of each dust can be generated by the difference between the pressure and the time required to reach this kind of pressure. So the level of Pmax is specific of each kind of dust. It is not easy to simulate also a dust explosion in order to try to find what can be the mitigation measures, because the Lagrangian model are not adequate to evaluate such consequence. Therefore, a CFD code is required. To run a CFD code, geometrical volumes shall be known. The turbulent flow of dust layers in some case can be not modeled properly, since the dust is modeled as a very dense gas, and it shall to be taken into account that the dust combustion process is rarely completed. There is also a fraction of non-reacting dust, which has to be estimated by means of assumption. So in several cases, it is not possible to model in a proper way a dust explosion, and the mitigation measures therefore are based on experience, on existing guideline standard and or literature data. What are the basically mitigation measures against potential dust explosion and fire scenario? For sure, fire segregation, fire rated walls that has to be provided to segregate the closest area where potential source of fire may be present. Selecting the rating according to the fire load. For waste storage area, it is required typically a higher fire rating than what is required in process building. A dust explosion protection has to be mitigated with the provision of explosion panels for equipment handling combustible dust. So in this case, there is not the prevention of the explosion, but the mitigation by providing some relief panels and explosion panel in the equipment and relief panel along the walls, in order to let the dust explosion can provide a way of escape without destroying completely the building. And of course, a classification of zone 1 and zone 21 and zone 22 in accordance to determine hazardous area and suitable for the out-ignition temperature of dust in order to minimize the source of ignition. The third example is related to the bio-based solution that has in some case the same criticality of dust, because The feedstock from which we normally start in a bio-based process is the biomass, so the wood chips, starch, hay, agricultural waste, and something like this. And this kind of feedstock has an high fire load and can generate potential dust explosions. In the intermediate process, which typically is consisting about hydrolysis, fermentation, and distillation, there are some chemical reactions that in some cases are exothermic and can generate runaway reactions, and also potential fire and explosion can be generated by the intermediate products, which are in any case, in several cases, are combustible. So all the safeguards related to a standard plant shall be taken into account. And the final product of the bio-based solution is biodiesel, ethanol, and solvents typically, and all these products are flammable fluid exactly as generated by a fossil fuel plant. So the high storage area of this kind of fluid has to be protected against fire and against explosion, and potential fire from this kind of products shall be considered and mitigated. From this kind of hazard that we have identified, what could be the real risk on which we are taking into account? The fact is the main risk is due to the fact that these process safety hazards are often happening in a context which is not the standard high hazard industrial context that is basically regulated by the Seveso III directive and all the other standards related to the Seveso III. In this case, we have several times the fact that we transfer high hazard risk in facilities which are not used to handle such kind of risk, because they are not regulated by the Seveso III, and in some cases, especially for hydrogen, could be even non-industrial but also civil facilities. So how we process safety aspects as process safety experts can act against this hazard transferred in new context? For sure, we have to start from training. We have to provide to the future managers and developers and operators of this kind of plant a specific technical and behavioral training regarding HSE and process safety. We have also to work on the updating of the norms and the standards, which in some sectors of energy transition are still not adequate. And starting from that, we have to adapt all the operating procedures and manuals, and to support the end users of these new plants to adapt their operating procedure to take into account a potential high hazard risk. And also in some cases, we have to adapt the process safety assessment techniques, because in order to properly simulate the potential risk of this plant, the standard technique of process safety like AZOP, SEAL, and QRA in some cases are not adequate, because maybe there are no PNID, there is no emergency shutdown systems, there is no possibility to model the dust explosion with standard Lagrangian model. So we have to take into account and to study new modalities in order to simulate properly the potential hazard of this new plant. And finally, we have to be aware and we have to be committed to the fact that there is the risk to having a new hazards and in a context that is maybe not used to handle high hazard risk. I come therefore to the conclusion. Energy transition for sure is a big challenge for the future and is of paramount importance to mitigate the climate change. We have not to underestimate the process safety hazard related to energy transition. We have to study proper safety assessment techniques and adapt to the specific energy transition sector in order to properly evaluate the mitigation measure. And we have to use an approach taking into account that the high hazard risk is in some case transferred in a non-hazardous context. I have concluded my speech and I leave the space to any questions that you may have.
Thank you, Maurizio, for your extensive and very clear presentation covering a number of issues. I imagine that there are several questions. We have not so much time. We are a little late. We have room just for one question, and we leave. Yes.
Yeah. Maurizio, just thank you for the very good overview and interesting talk. There was one item I was interested a little bit. I was triggered. When storing hydrogen, you're mentioning carbon steel is not a good material, as the hydrogen can get into the steel and make the steel brittle. And then going to other plastics might be a solution. But then you mentioned that the higher pressures, the plastics might not be a good solution. That would, however, be very nice, that if we can create a containment out of non-iron, let's say, plastic materials, also at higher pressure. What kind of options do you see there, and do you really feel this is not possible?
No, let's say, from what is concerning the storage of hydrogen, in particular taking into account the big amount of hydrogen, the first recommendation that is coming from hydrogen experts and also from hydrogen storage, I would say, producers, is to store as less as possible. That means that the storage of hydrogen by himself is critical. Then, of course, if we have some storage at at low pressure, that means a pressure up to 12-15 bar G maximum, above which the materials like polyurethane resins or FRP or GRP are still not tested. That does not mean that they are not suitable, but at least they are not certified. So at this level, we can store with some kind of tanks that are not done of steel, because of course, if we store a big amount of hydrogen with steel, we have to use stainless steel, and we increase a lot also the cost of storage, because you can imagine plenty of tanks done of stainless steel instead of normal carbon steel. Of course, a secondary containment could be positive, but you have to consider that in case the embrittlement is generated within the boundary of the tank, there is the risk with time to destroy the entire tank. So also the secondary containment cannot be an efficient solution, because hydrogen in any case is a gas that is volatile, that is very volatile. No? So the suggestion is to consider, first of all, the maximum amount that you want to store as hydrogen, trying to limit as much as possible the storage, and to instead maybe increase the capacity of electrolyzers or the capacity of the downstream plant in order to put the hydrogen as much as possible in other different forms from the subsequent plants and so on. In case of storage, there are still some possible solution to be investigated, like some bullets that can be even mounted, that can be made of non-metal, but there is also a very big lack of standard on this case. So there are still no standards that are regulating in a proper way how to store correctly the hydrogen.
Thank you, Maurizio, also for remembering us that the old lessons of Koerts regarding minimization and intensification is still valid.
It's still valid, absolutely. It's still valid.
So we can move to next speaker. Sorry. Okay. The next speaker is Dr. Tjis Koerts. He has been product manager and process safety management team leader at DuPont de Nemours in Dordrecht and Geneva. Subsequently, he was operational at manager LyondellBasell Industries in Moerdijk, and currently he is senior process safety consultant for the hazardous processing industries, including HAZOP, LOPA, sea latex, incident investigation, auditing, and coaching organization to achieve HSE excellence and lead culture change programs. He is currently the operation director of the European Process Safety Center, and he is leading the process safety interest group for the NAP industry. Additionally, he is permanent guest member of the Loss Prevention Working Party of the European Federation of Chemical Engineering, and he is engaged in improving process safety culture throughout Europe by organizing an yearly process safety conference. So please, guys, the floor is yours.
Bruno, thank you so much for the kind introduction. Lots have been said already. Let me spend 2 words on the European Process Safety Center, where I spent most of my time. That was founded after the Bhopal incident, where the industry said we need to do a better job in protecting society, and that is still our mission. We've arranged a legitimate network between industry members to talk to each other, and we basically just talk about industrial best practices on how to handle hazardous components in the best safe way. For those who don't know the EPSC strongly, try to visit the website one time, epsc.be, and at least get registered on the learning sheets. Each month we'll make a learning sheet of an industrial incident, and we talk about the critical aspects here and basically the good industry practices on how to avoid these incidents. And even when societies might be high level on management system, it is very good to stay connected to this reality and discuss this reality among members, keep it sharing, and it's the learning sheet are translated in many languages, among that Italian, but also Chinese, Arab, and this week also somebody out of Thailand offered to translate them into a new language. Just a little bit about numbers. We've spoken about the need to change. So as industry, we had problems with acid rain, and the acid rain was solved. We had problems with the ozone layer, and we solved the issues with the ozone layer. Now we have issues with high CO2 emission, and people might expect from us that we solve this, and we will have to solve this, but it is a more complex problem. It's a much bigger problem, and there's much more to do to change, and far more people will be involved in this. This is a little bit the role of the industry in producing CO2. So some numbers: 27 gigatons of CO2 is produced in the globe, and you see so there's something on transport. Building the concrete is producing a lot of CO2. And at the same time, industry is doing a major part. So the largest part is industry, and there's a lot of focus to change things there. So steel is a quarter of the industry, and that's a thing. You see the other part, that's the refineries and so on. So industry has a major part to do. About 10 gigatons of CO2 is related to them. Here you see a little bit the role the CO2 popping up. So in the beginning, just before the Industrial Revolution, we were in the order of 250 ppm CO2 in the globe, which in the 1850, and you see that number is slowly on doubling now to 420 ppm of CO2 on average on Earth in this decade already, and still going up, and that is an issue. That is an issue. It would be good to understand, but if this doubling is going on for 2 more times, the CO2 concentration is so high that it is from a hygiene perspective. People say you cannot work in that environment for 8 hours in a row. So then also it becomes a toxic thing to people. Right now, people feel mostly threatened by, of course, the global warming and the increased amount of energy which is on Earth. So we have to do something. We need to go to away from CO2, and the answer here is really, the answer is hydrogen. Decarbonization means hydrogen, and hydrogen has several new aspects there, and the two major incidents are plotted over here. The Hindenburg incident, where a Zeppelin is getting on fire, and of course hydrogen is the most ideal gas to put in the Zeppelin because it's the lightest gas that we're having. And at the same time, you see the problem with the hydrogen. As soon as it is released and mixing with air, it is a great flammable substance, and you can have a nice fire, creating a lot of heat and a lot of consequences there. The other one is the Challenger incident. There, when we launching rockets, then we trying to be as condensed as possible in our heat, our energy balance, and hydrogen is the answer there. The good thing of hydrogen is it is a very energy condensed substance, especially when you compare it versus weight. With a kilogram of hydrogen, we can easily drive 500 kilometers on the road, which is huge versus hydrocarbons, of course. So in terms of energy packing, condensed, it's a great substance. Here we had the hydrogen stored as a liquid, and then it's extremely cold, and then the liquid got leaking through an O-ring, and then it mixed with the oxygen and it exploded. It's interesting to see how people were looking to these incidents. In the Hindenburg case, people said, well, putting hydrogen in these Zeppelins is maybe not what we want. Let's put the safer helium gas in there. And helium is far more expensive than hydrogen, which made flying with these Zeppelins very expensive. And basically we stopped doing that. We started flying with helicopters, with other means, which are all producing a lot CO2. So still the question is there, can we not go back to Zeppelins and make sure that the hydrogen is in a much safer way there, and that we avoid these serious incidents, and be able, for example, to transport goods through the air in a very low cost manner, without producing very little CO2. Or no CO2, because the hydrogen can be used to drive an electrical motor. And then the other incidents for the Challenger, there we consider to accept that hydrogen is the required fuel. We don't change the liquid hydrogen to something else, because these rockets would never be able to lift off. So we are stuck to hydrogen, and we just understood we need to improve on safety. So the more critical thing is how to make hydrogen safe, how to go to decarbonization. And yes, we will face incidents with hydrogen if we go to do the energy transition. But realize that we have probably had millions of fires with hydrocarbons that were not wanted, and from each fire we learned a little, and from each fire we made another step. So there's a lot of experience, history, and understanding on how to work safely with a hydrocarbon environment. And we still have to learn in the energy transition on the new hazards, and one of them is working with hydrogen. what the previous speaker already indicated, what were some key things from hydrogen? The first thing is that a fire, you don't see a hydrogen fire very easily. So on the left photo, you see the hydrogen. There's a hydrogen fire, but basically during the day you won't recognize it. While if you just would look with an infrared camera, then you see on the right you can detect the fire pretty easy. So that's the first thing. It's a hazard. You can see a fire during daytime, but there are solutions that you can implement there to learn working with this and to easily get alarmed with hydrogen fires. The other one is on reactivity with hydrogen. If we go from natural gas to hydrogen, and especially in the UK, there done many studies. Then there are two aspects. The first one is that the molecule of hydrogen is much smaller than natural gas, and its ignition energies is order of magnitude smaller. And natural gas is a relative stable molecule, which is not easy to start getting reacted with oxygen. You really need to go for quite some energy to put quite a bit of energy in there. While hydrogen only needs a very little energy to get started. So that will be a major challenge if you put hydrogen into a natural gas work and you leak a little bit of the hydrogen, then of course the likelihood of ignition is completely different. The other aspect of hydrogen is its high reactivity. And especially in industry, what are we afraid of? A gas explosion we typically survive, but a detonation is what we're really afraid of. If we have detonations, you have these overpressures of 10 bars, and you cannot design for a detonation. A detonation is blasting your building away, and you cannot stop that. And unfortunately, hydrogen will easier create a detonation than natural gas, and that has been proven now. So that is a thing where we need to start to live with, and that requires some thinking in design, but especially it might require higher standards to avoid leakages with hydrogen versus what we have these days with natural gas. So that are the two things that the previous speaker also indicated. I like to bring you a little bit in the production of hydrogen that we really need to understand. If we want to go to change to the hydrogen economy, at least we need hydrogen to be present so we can start working with it. And the easiest way to create hydrogen in larger quantities is by steam methane reforming. So you take natural gas, you put oxygen or better water with it, and you bring it to high temperature, and you create hydrogen and CO2. So the good thing is you have quite a bit of hydrogen available. The bad thing is you're still producing CO2, and then that is called gray hydrogen, as it is not very nice. Now you can make that gray hydrogen blue if you separate the CO2 and you say, hey, let's put the CO2 under the ground. And we have a lot of oil, natural gas that we take out of the ground. We put the CO2 back in it. Then we have this what we call blue hydrogen. And at least for CO2 perspective, this is good. And it might not be bad to do that for a generation. So at least we can learn to start working with hydrogen, while at the same time profiting from the fact that CO2 is not getting into the air, while still having the energy of the natural gas resources, and we can still continue to use those. You can also pyrolysis of methane. Then you can transform methane into hydrogen and carbon, and then you can store the carbon easily as a solid. The final way of hydrogen where we need to go to is using it from solar. So getting electricity from solar and then store the solar into hydrogen. That is what is called green hydrogen. You see the electrolysis cell there, and effectively we are start building these electrolysis things right now. What are the new hazards there? There are membranes in there, and if you have a bit of hydrogen permeation through a membrane, you can imagine that the hydrogen and the oxygen will end up at the same area, and that you create a hazardous environment. So yes, you need to keep these well separated. You need to have some validation that your membranes are in good shape, and hopefully we can produce these membranes in such a way that this will not become a large threat. So again, summarizing, hydrogen is a great alternative as energy carrier to avoid CO2. You can easily produce electricity with it, which is great. So also for electrical cars, if you instead of getting a large battery in there, you can also put a little bit hydrogen in there, an electrolysis cell, and then you can create cars in that way. The flammability remains, and it's explosive versus methane is even worse. The bad thing about hydrogen is it's hard to transport it over large distances. Just like methane, over short distances you can transport it in a pipeline, but over larger distances people prefer to liquefy it. For natural gas we do that. We have a GTL process, gas to liquid process, run in Qatar, where we take natural gas that we then change into hydrocarbons that are liquids, and then we use those to transport. Natural gas by now can also be transported by cooling it down to -180, and then you can transport it in a ship and put it in a vessel. And we've built quite a few ships and vessels to do so. For hydrogen, that's more difficult. Liquefy hydrogen, it costs an awful lot of energy, and it's just very difficult because you're very close to the absolute point of 0 degrees Kelvin. So for hydrocarbon, for making it, to liquefy it, what we could do, of course, is transform it into ammonia, and then you transport the ammonia, and then you create the hydrogen out of the ammonia back. That's technology which is getting available readily now, and yes, we can do that. Of course, the hazard there is ammonia is toxic, and you want, especially if we do this large scale, then you need to stay away from the areas where you store these toxic ammonia. So that will be an issue. I'm not sure. Let me show you two quick pictures these days. So what you can do is take solar power in Australia, transfer the solar power into hydrogen, liquefy the hydrogen, and ship that to Japan. So there is a carrier now for liquid hydrogen that is going to do that, and that's the first step. Another way of doing these days is creating blue ammonia. So we get a lot of oil and gas from the Middle East, and these guys are willing to say, hey, if you don't want the carbon and just want to get the hydrogen from us, we can deliver that. We can take the natural gas, take the hydrogen out of the natural gas, connect the hydrogen towards ammonia, liquefy the ammonia, and put that in a vessel and ship that to you. And then the ship that arrives is not having crude, but it's having the liquid ammonia. You can store the liquid ammonia and get the hydrogen out of it. And basically it means we can start this hydrogen economy pretty fast. And in the meantime, Saudi Arabia will put the CO2 that they produce under the ground, and from there on you would have at least a closed loop in terms of sure, not fully decarbonized yet, but basically if we want to start today and make a big step towards to decarbonization, at least not putting CO2 in the air, we can make those steps. And that's a big transition. There will be some cost involved, but we can do if we want. Let me do this as a last slide because my time is up. As the EPSC working group on the new hazards of the energy transition, this is a little bit the aspects that we are working. A lot of it is focused on hydrogen. We were talking about CO2 capture and putting that under the ground where new hazards are related. This is gas to electricity combined with co-generated with steam. So the cogens are cost effective. Lots of things about new feedstocks that we talk for biofuel. Solar on sites, storing ammonia is of course an issue. Batteries is a chapter by itself. All the batteries being used, the new hazards from batteries, there's stored energy in there. And unfortunately, there's also a little bit of electrolyte, and the electrolyte can burn. So batteries can burn, and we know that, and we have seen occurring that quite a bit. So that's still the thing where we need to improve the technology. Lots of things on biogas where we can do a lot. Recycling of plastics where we can do a lot, and that's a little bit the focus areas of the EPSC right now. Bruno, to stay in time, I like to leave it here and maybe answer a few questions that people might have.
Thank you, Tjis, for keeping the time and for providing us so wide view on the implication of decarbonization and energy transition. Now there is room for some questions from the public. No question. Just a comment. Do you believe that in the total risk, in the whole risk assessment procedure, which is the weak point in the energy transition, hazard identification or scenario, or in your view?
Well, I think that the hazards are not that new. So the hazard identification is maybe not the big thing. Where we all the properties that are being mentioned now by everybody from hydrogen, all these properties we know by 50 years. There's nothing new. Same for ammonia. It's toxic. We know exactly how toxic it is. So doing QRAs with these large storage facilities of ammonia is of course something that is also not that difficult. I think the most it's a public opinion. What we will do is we will have new incidents with hydrogen. We will have new incidents with ammonia, and the acceptability from the public, that's where an issue is. If the public wants to say, hey, we want to have something which is absolutely safe, with zero incidents, and that's the only thing we want, that is a hard thing. I mean, there's always compromises in here, and we need to get the time for a learning curve. So yes, we will have incidents, but we will go to improve. It's the same thing like learning a car to drive. Yes, the car will make some incidents and we will have some fatalities there. But in the end of the day, a car driven by a computer will have less fatalities. So the driving of a car by a computer will be much safer in the end of the day than when humans are going to do that, and we will we will save many lives by doing that in the end of the day. So for environment, it's the same thing. There's no option to say, hey, do we want to save the environment or not? It's a must. We have to do that. That's basically the story.
Thank you, Tjis, and thank you also for the initiative as a director of the European Process Safety Center of disseminating the learning sheets that for sure raise the availability of information and allow to improve, let me say, risk perception by the public and understand the lessons. So thank you once again. Now we can move to the academic part of this webinar, and we start with a top researcher of well known throughout the Europe and world, and he is Professor Valerio Cozzani, who is Professor of Chemical Engineering at the University of Bologna, and where he leads the Laboratory of Industrial Safety and Environmental Sustainability. He has several years of experience in research and process safety, sustainable design and technology, innovation in chemical processes, and he led several international research projects, both funded by public organizations such as the European Commission, Italian Ministry of Education, Italian National Civil Protection, Regional Environmental Protection Agency, and private companies, just to mention one, Shell, Eni, Lyondell, Basel. He is member of the Working Party on Loss Prevention of the European Federation. He chairs the ESRA Technical Committee on Chemical and Process Industries, and he was recently appointed as chairman of the section on energy of the European Federation of Chemical Engineering. So he is just the right person. So please, Valerio, the floor is yours.
Okay, thank you, Bruno. Hello to everybody. Just to be sure that you can see my screen.
Yes. Thank you.
Is it showing the slides? Yes, because, okay. Just a minute, I'll share again it. Okay. Yeah, sorry, because it gave me, okay. So thank you for your very extended introduction. Welcome to everybody to this short speech. I'll try to introduce you to the problems that arise when implementing what we feel as new and green, environmentally safe technologies, but actually that while preserving the environment from the threats due to climate change, can introduce new type of hazards in the society. The presentation will first briefly recall the objectives and framework of the transition to sustainable energy. Then we will briefly recall the problem of safety of energy technologies that was already discussed by the previous speakers, and then specifically look at, with some quantitative data, the problem of the trade-off of risk that I was mentioning. And finally, a few ideas about the problems of risk governance in the energy transition framework. Concerning the first point, we have already clearly in mind the problems that lead the energy transition process and the decarbonization of industry. In this framework, it is very important to address the shift from conventional fossil fuels to renewable energy. In the future, there will not be a single type of renewable energy that will be exploited, but rather the combination of a number of different energy sources. This makes the landscape of energy production more critical. it should be remarked that the main difference in this transition is that renewable energy sources are variable and not programmable. That means that the green stability requires the implementation of advanced and innovative methods, and that the penetration of renewables requires technologies for energy storage. Now, beside batteries, one of the more attractive type of procedures and technologies for the storage of energy is the conversion of electric energy to chemical vectors. This is sometimes called chemical storage, but when these energy vectors are not converted back into electric energy, but rather directly used, we usually mention these processes as power to X, power to gas, or power to liquid. In this framework, there are a number of technologies addressing the possible production of methanol, of ammonia, of hydrogen, and other types of energy vectors. As mentioned by the previous speaker, hydrogen is for sure the most popular, and it's proposed both for urban but also for domestic applications, so not specifically for industrial applications. And the other point, the other type of attractive energy vectors that has a high technology readiness level is ammonia, which is proposed especially for long-range transportation and ships. It is also important to remark that this change in the landscape of energy and this use of chemical energy vectors as hydrogen, ammonia, methanol, and others is not a matter of industry. Meeting the carbon dioxide emission reduction objectives actually requires the decarbonization of domestic applications as well, and of private transportation. So we all are concerned personally on the one hand. On the other hand, it is important to remark that this transition will not be something that will take place in industry, but rather that will change our residential areas, our infrastructure, and our transport, our public transportation, our buses, trains, ships, and so on. This causes a big and important difference when coming to the issue of safety. And also, by the way, of technology more in general. We have a huge operating experience with hydrogen and ammonia. But however, all this operating experience dating for several decades is mostly limited to industrial use. Now, when you are in industry, you have trained operators, clearance areas, you have limits to simultaneous operations allowed in the site, and you have implementation of specific technical standards as ATEC, for example, which will limit the ignition sources. This is not what happens when you are in urban and residential areas, where you have a totally different scenario. Now, what does this mean? We are quite aware about the concerns with respect to safety that energy technology pose. However, we may we could be confident that the shift required in the energy framework by the advent of renewable sources could get us free of the safety concerns associated with fossil fuels. However, this is not the case. This is not the case, but rather in the energy transition framework, we will have to face, on the one hand, the problem of the overall sustainability of technology, and on the other, the problem of the total risk profile of technologies and the problem of awareness of risk that is caused by these new sources. Safety of energy technologies is actually a key requirement for their societal acceptability. As an example, in Europe, we are complaining now, we are facing a shortage of natural gas, and we are complaining that we don't have enough regasification capacity. But we must recall the huge societal opposition that the installation of new regasification plants faced, especially in Italy, but also in other European countries. So if we want to implement an energy technology, we need to grant a societal acceptability, and this is based on safety scores of the energy technology. Now, when dealing with fossil fuels, we have, unfortunately, hundreds of sad stories and severe accidents taking place not in industrial areas, but in residential areas. Here I have a couple of examples, one in Belgium in 2004 concerning a natural gas pipeline that was cut during excavation works. And here another example in Viareggio in Italy in 2009, where an LPG freight train derailed outside a railway station, and an LPG cloud spread on houses, causing several 10 fatalities. So this is the current situation with fossil fuels. What about the future situation? Well, in the future situation, it should be remarked that some of the new technologies for energy may create what are called emerging risk. Emerging risk is a new risk, but this is not the case, but rather what is happening is an increasing risk in this definition. That is, the likelihood of exposure to the hazard leading to the risk is increasing due to the spread, to the foreseen spread of new energy technologies, and in particular of the exposure of people in urban and residential areas to the hazard caused by these new energy vectors. These concerns are clearly demonstrated by what we can call early warnings or weak signals that we can collect. As an example, this final report from the European Commission, which states that the use of hydrogen storage on board vehicles remains a challenge due to the requirements of safety. And here you have another weak signal. An accident occurred in Norway in 2019, where an explosion caused by a hydrogen leak at a fueling station caused an explosion with the projection of fragments on a public road. And here you see cars that are still around just after the explosion took place. And just by chance, nobody was hurt by this fragment projected away by the fuel station, which you see here in the picture, still on fire. When this happened, there was even uncertainty by the emergency responders about which could be the safety distances and which could be the emergency intervention plan to put in place to mitigate the accident and stop the fire. As a result, the company involved withdrew from hydrogen distribution business in Norway. So you can see how safety can interfere with business plans and with the implementation of these energy vectors. And this means in perspective that safety can be a limit to the energy transition, or at least needs to be considered as an important factor driving the transition. It is important to look at the safety perspective in the framework of risk trade-off. Actually, We are looking at this energy transition towards sustainable energy in the framework of risks caused by climate change, which we have on our forehand, and that that are posed with respect to supply chains and economic activities in several countries. We have this, these were discussed in detail in the COP27 conference that ended these days in Egypt. But when implementing this transition towards renewable energy, energy vector, and decarbonization, we need to consider the other risks that we are introducing. So there is a kind of trade-off. That means we need to find a balance between the benefits and potential side effects in the domain of environmental risk and of process safety and occupational safety for the technologies which we want to introduce in the framework of energy transition. If we give a look, taking an example, maritime transportation, what we're facing is a pathway that leaves marine gas oil, that was the standard solution only 10 years ago, towards the use of liquefied natural gas as a fuel. This was the first change introduced, and there are several ships implementing nowadays this concept. But then there are the new concepts: liquid hydrogen, compressed gaseous hydrogen, cryocompressed hydrogen, and liquid ammonia. All these are alternative technologies that may be considered for application in this new framework for energy transition. When facing this change, we can try to introduce key performance indicators that may help us to capture the impact of these technologies, on the one hand on the environment, and thus in perspective on the perspective of climate change, and on the other hand on the other domains: technical domain, economic domain, and safety domain, due to the features of these new technologies. Here you can have an example of a procedure to assess key performance indicators that can be applied to the conceptual or early design stages of technologies. Just to focus on what's inside these procedures, there are usually models applied to the calculation of specific indicators, and here you have an example for the safety indicators, in order to assess some parameters representing the impact. In the case of safety, these are the safety distances and some credibility factors for the accidents that may take place. When applying this framework to perspective technologies, you can have results that may allow you to compare which can be the performance of the technologies on specific issues, as the point of view of safety. And here you have the results of inherent safety key performance indicators calculated for a bus. So bus transportation, where we tried to apply the different technologies proposed, implementing storage tanks having the same mass of fuel. That means more or less the same, that the bus will be able to run the same number of kilometers with the amount of fuel that is present in the tank. When calculating the safety performance, this indicator provides you an impact indicator. So it's the higher the indicator, the higher is the risk associated to the technology. The blue indicator is a potential hazard, so not considering safety systems, while the orange indicator considers the generic protection introduced by standard safety systems. Well, what is important in this plot is that you can see that the diesel fuel here shows a near zero impact. That means is definitely safer than any other alternative type of fuel. And even when considering liquefied natural gas, this ranks hazards that are lower than compressed hydrogen, cryocompressed hydrogen, as this CC, liquefied hydrogen, which all show higher risk. And so a less inherently safe behavior. When extending this type of analysis to other domains, and here you have a second example for ships, where we considered technology indicators, the red one, economic indicators concerning the cost of the technology, environmental indicators concerning emissions, and safety indicators for different technologies, you see that this approach provides a performance. All performance here is negative. That means the lower is the value of the indicator, the best is the technology performance. And when you look at what comes out, focusing on the environmental impact and on the safety impact, you can see that fossil fuels that are marine gas oil and liquefied natural gas have definitely a much higher environmental impact than all the alternative fuels, in particular hydrogen and ammonia, that were supposed to be obtained from renewable energy sources, but still the risk detected by the inherent safety indicators with most of these technologies is much higher than the one from conventional fuels. So definitely what we are doing is to operate a shift in the risk from the environmental compartment to safety when introducing these new technologies. So we need to govern, to balance this risk and to govern this transition, taking into account that this new risk is not inside an industrial site, but rather will be distributed in infrastructures. How can we cope with this problem? Well, as I mentioned before, in the framework of energy transition, management of risk is complicated by a number of factors, as the need to manage different type of risk, transition time frame, uncertainty due to the limited information available on the new technologies. So we need some strategic orientation and adequate decision support tools. Just to mention, to provide a few more details on what I was mentioning, you should consider that in perspective, we are facing a transition period in which the old infrastructure based on fossil fuel will come and exist together with the new infrastructure. And this transition period is even in the more optimistic forecasts will last a few decades. We also are looking at solutions as ammonia and hydrogen that have low technological maturity when applied to some specific application as transportation or some new industrial applications pertaining to the decarbonization of industrial sectors. And finally, the regulatory frameworks which we have were built to regulate the use of these energy vectors in an industrial context. So we have the lack of specific regulations outside industrial sites, and this may be a problem in the authorization and implementation of new technologies. We can, in perspective, we can think that we can use some principles to develop the new networks that we expect will be required for energy vectors. Here I have reported the gamma principle, Globalement Omen Ossibon, that is a principle that has driven the implementation of the high-speed railway network in France, where each new technology implemented was required to have safety performance that had to be always equal or better than the technologies that were substituted or that were present in the former railway network. This principle can be of use when implementing new hydrogen networks, for example. At the same time, what we need to look at is the societal risk. And we have indicators, as the FN curve shown here, that are able to capture how in a local community the risk, there will be a risk to which the population is exposed due to multiple risk sources. Now, the implementation of a new network will cause an increase of the societal risk in this new landscape, in this new framework. It is important to understand that this indicator will become crucial to warrant to the local communities that the new energy framework will not come at the cost of an unsustainable or unacceptable risk for the population. It is also important to mention that in this energy transition, we have the possibility to introduce a risk governance that will also be able to address new opportunities. In particular, if we build new energy infrastructure, so we can implement principles for their adaptation to climate change. And we can implement safety 4.0 principles. That means principles that may help to enhance the safety of the digital technologies that will be associated to this new energy framework. Finally, coming to some conclusion, the energy transition and the diffusion of hydrogen and other energy vectors in urban and residential applications are expected to strongly influence the safety of workers and population, and may be a limit to the energy transition. So we need to implement appropriate risk governance in this energy transition process and to recognize and balance the risk trade-off from the environmental compartment to the societal compartment. New knowledge and the rapid evolution of the regulatory framework are required to assure this safe transition. And if we will be able to do this, we should also have in mind that the energy transition is also an opportunity to develop and implement safer and more resilient, digitalized, sustainable energy technologies. Before ending my presentation, I would like to acknowledge the contribution of Francesco Zanovetti, Alice Schiaroli, and Alessandro Dal Pozzo, three of my co-workers, to this presentation. And I would like to thank you all for attending, and obviously I'm available for questions, if any.
Thank you, Valerio, for your presentation covering the important issue of the trade-off in the energy transition and the novel risk management implication and possible strategies. So we have room for one question, as we are just in time. Any question from the public and the delegates? As you are an academic like me, do you think that the students need to be the student curricula need to be need a modification to force, let me say, students to think holistically to the problem, or you think that our curricula are already prompt and ready for the energy transition?
Well, transition also in university curricula would surely help. Our students, I think, will be the key workforce and the key intelligence to introduce in organizations the energy transition. So they are a key resource to implement these new energy technologies on the one hand, but also the new safety culture that needs to be carried together with this. So I don't think that a big restyling of a curricula is needed, but for sure a higher emphasis on some problems might be needed, especially considering that in many curricula we mostly look at industrial risk when dealing with technical risk. We don't look at risk in residential areas, in urban areas, and concerning let's say, the cascading events that may derive from technical accidents in critical infrastructure as the transportation network or other similar networks that will be affected if we modify the fuels that we will be using on for the road transportation on trains and ships and so on.
Yeah. Bruno, I think it's an outstanding question.
Yeah.
Because it's new and at least 50% of the people we are delivering from universities these days are going to work in the energy transition. Their main role is to get this happening. In the old days, people were working to oil and gas and plastic manufacturing. The first thing, people don't want to do that anymore because it's a dead-ending street. And the second thing is it's the likelihood that you're going to spend your time in there is much smaller. So I know people in universities changing their curriculum is not an easy thing. People always have quite a difficulty in optimizing this, but getting more of the work we're discussing in here and introduce that in the curriculum would be a very good thing. Realize the next 30 years, so the people which are now in universities are only going to work on this on making this energy transition happening.
Thank you, Tjis, also for the industrial side of the problem. And so we are going to end our webinar on a high note with a combined presentation. The first speaker is a guru of process safety, is Professor Hans Pasman, who is a professor at Mary Kay O'Connor Process Safety Center at Texas A&M University and emeritus professor of chemical risk management of the Delft University of Technology in the Netherlands. He originally joined the Dutch Organization of Applied Research, TNO, where he did or led many investigations into disastrous industrial accidents, and he initiated and led research in reactive materials, explosions of all types, and risk analysis. He was chairman of the International Group on Unstable Substances for 10 years. He was the chairman of the European Study Group on Risk Analysis and the NATO Group on Explosives. Since 1972, he is a member of the Working Party on Loss Prevention and Safety Promotion in the Process Industries of the European Federation, and he was the chairman from 1986 to 2004, a very long period, and he made the history of the Working Party. The second speaker from the same university, Mary Kay O'Connor Process Safety Center, is Dr. Edison Sripaul, who is assistant director and senior researcher. He earned his master from the University of Waterloo, an MBA from Laurier University, and a PhD from Memorial University. He performed extensive research on the characterization of reservoir fluids and rock, as well as other porous materials, along with energy storage, CO2 capture, and alternative energy sources. Edison is a member of the Society of Core Analysts and the American Society of Chemical Engineers, and is a registered professional engineer in Canada. So please, Hans, you can start your presentation.
I shall do the first few slides and then Edison will take over. But we made together the whole presentation. And well, the presentation, of course, covers a number of topics that we have heard before: new energy sources, carriers, and storage. But you will see also some differences. Okay? Can we have the next slide, Edison? Right. Mary Kay O'Connor Process Safety Center is because Mary Kay, the wife of Michael O'Connor, died in an ethylene vapor cloud explosion at Pasadena, Houston, in late 80s, 89. And well, in fact, it was a shock in the American industry. And it moved Michael O'Connor to donate to the university where he had been in the past an amount to found that center, Process Safety Center. And well, still goes on with a large steering committee of industry people, mostly. And the research teams, well, started with the process safety. That was the main thing in, well, 95, and then in 1998, a new director came in. Then risk assessment is getting now also a very important item, because in the meantime, there is a new director, Dr. Faisal Khan. We started in cyber, physical, and system safety. Also, of course, a lot of cyber security. And then the last few years, it is going also in energy safety. The next slide.
Sorry, Hans, may you raise a little the volume?
Yeah, sorry? Oh, the volume.
The volume, just.
Oh, okay.
It's rather low.
Let me, then I have to, just a minute. Then I go to here. And I have here, is it better now?
Yes, yes. Thank you.
Yeah, okay. Then, okay, I will not go into very details here, but you can see that the 4 directions split into many sub-directions. And, well, hydrogen is there, batteries are there, electrolyzers are somewhere also. Okay, we go to the next slide, and that is a little bit on safety fundamentals for a few definitions. And then Edison will take over on energy transition. You heard already quite a bit on that. The energy carriers, hydrogen, ammonia, electrification. We will talk quite a bit on electrification. Energy storage, batteries, fuel cells, and concluding remarks. Okay, next slide. And well, that is again on the hazard and risk. A lot of people are not aware very of the sharp difference that is there. Hazard is a potential, and it can be without a trigger, can stay there for ages, so to speak. But risk is a combination of the consequence if that hazard unleashes, and the probability, likelihood that it could come. And that depends on a lot of conditions. And then there is personal safety and process safety. Personal safety is of course, well, it's also known under the name occupational safety. It is, not all the way acute. It is also because of permanent chronic toxicity, for instance, if you are working in a certain environment. While process safety has to do with the safety of the socio-technical system, well, the plant, but also the organization and the people that are in that organization. So, right, there is quite a difference, and that is, well, in the past, not always meaning that the process safety was given sufficient attention. What is health now, and what is safety? Absence of illness and sickness, that is clear, but safety is absence of accidents or losses, hence risks. How to measure and maximize? Yeah, that is, first of all, check for any illness or sickness, risk acute toxicity, and for the process safety and safety in general, I should say, check for any accident causing a situation. So a risk assessment. Now, risk assessment, you think in the first place of a whole plant and facility, but you can do as a person also a risk assessment for your personal safety. Minimize risk, avoid unhealthy work conditions, minimize system risk, and analysis, prevention, and protection. And we have a lot of methods for that. Do regular checkups in your health, but for process safety and other safety, monitor and manage risks. And that is in the digitalization age. There is an enormous development going on in dynamic following and seeing what risk we run. Okay. Safety to the system is health to the human, and that is introducing the energy transition that Edison will treat. Please, Edison, go ahead.
Yeah, so during the Industrial Revolution, we saw the transition of energy from wood to biomass or coal, and with the growing industrialization, we saw the advent of oil and natural gas taking over the whole industrial world. So with the Paris Accord and the net zero demands to be met by in the next 50 years, we are looking for a new energy transition that will help us to reach this. And hydrogen is touted to be that next fuel that is going to help us reach that 2 degrees centigrade ceiling. So with the new urbanization, the consumer demand, and the need for the great energy, we're looking at hydrogen to replace it. But when we get into that regime, what are the new safety hazards that we are looking at is the big question that needs to be answered. With the new energy demand in terms of hydrogen, we are looking at large-scale electrolyzers in industrial scale. And again, the large amount of or the volume of the hydrogen, and again, the production of oxygen in the same process is going to be a simultaneous process where we are looking at new hazards and the capability of accidents that will actually impact the human population. The other aspect of ensuring we reach net zero is through process electrification of the process plants, which essentially will help us mitigate the CO2 emission to the atmosphere. So essentially that will be one aspect that needs to be looked out to make sure that we reach the demands required by net zero. With these new transformation in technology, we are looking at new risks, and as we are evolving, we are slowly finding out what are the risks that are coming out, and many are still yet to be found. So if you look at hydrogen, we see it replacing the other conventional fuel. If you want to be green, then we're going to use the renewable sources like wind and solar energy to provide the power to power the electrolyzer, which will help us produce hydrogen. that hydrogen, again, the energy that is produced has to be stored and has to be transported and to be used for the end users, like heating up buildings or to power our cars and automotives, and produce chemicals and fuel that are required for further use. One sector that is largely looked at is the transportation, or the large-scale transportation like trucks, which will actually help us to reach towards the goal of net zero. This is looking at one way of safely securing this whole process. If we are to prevent any major catastrophe in a highly dense area, the whole production of green hydrogen is moved to offshore wind farms, where the wind energy supports the electrolyzer powering to produce hydrogen. Then it can be transported onshore to be used for consumption. But then as we try to mitigate all the risk, then it creates a new risk, which becomes the cyber threat, which we have seen in the last few years, where major companies have been threatened by the cyber attacks and then ransomware. So this is one thing that again has to be looked at before we even go into this direction. If you look at the whole scheme of it, we have layers of risk and analysis being done. The whole wind energy used for hydrogen production, which eventually be used to produce another energy source, which is the ammonia. So if you look at it, we have the data reliability and resilience that is carried out throughout the whole process, and then understanding the safety and risk aspect of it. Then we also have to look at the cybersecurity and safety aspect, because that oversees all these aspects, and then make sure that this whole hydrogen production runs seamlessly without any issues. As we get into hydrogen production and then transportation, storage, and then eventually end use of it, we're looking at different regulators coming into play, especially when it comes to vehicles. We have the Society of Automotive Engineers overlooking most of the regulatory aspects related to transportation in terms of vehicles, usage in containers, reformers, and services. When it comes to dispensing, again, the process of dispensing it to commercial use, it comes to, again, material aspects. ASME, CSA, and NFPA have the regulations overseeing all these aspects. The storage equipment have to be built according to standards, and then ASME is one standard that is often used for all these process equipment all this time. And again, they play a major part in ensuring that the storage containers are built according to the standard. We have a mixed number of regulators coming into ensuring the infrastructure according to the regulation and the standards are met. So if you look at it, there is major players in terms of regulators who are ensuring or monitoring the safety aspect of it. But what needs to be seen is a big entity or one entity overseeing all these aspects to ensure that there is uniformity and able to actually maintain this regulation when it transacts different aspects of the production, storage, and dispensing. Once again, when the energy is produced, to be able to be transported and delivered to the end use, have to be stored in some ways. And we have seen the evolution of different storage mechanisms like electrostatic capacitors and electrochemical capacitors. Batteries are largely used these days and becoming mostly growing in terms of meeting the demands of cities' power demands by making large-scale battery farms. If we are looking at transportation, then lithium-ion batteries are really growing as the need for the electrical cars comes into play, and the countries that are trying to ensure that in the next 10-20 years, most of the transportation is going to be electrical. So this again opens another facet of safety question as what happens to the battery safety. So when you have any thermal runways on a anhydride formation, it results in spectacular explosions like you see on the picture here from New Delhi, where just the electrical cars stored in parking for delivery in extreme summer, they're not able to manage, and then we have explosions happening. And once they start the fire, we don't have a current protocol to put out the fire except to watch it burn down. Although we have the battery management system to model how the batteries will be operated within the safety limit during charging and discharging, but due to the changing climate and other factors, we're still not able to ensure that they will operate within the safety limit. As we move on, then ammonia tends to be the next other energy that can help us reach the goals for the net zero. It has emerged and has been in the use in the industry for a long time, but it is not in a large scale that we expected to see in the next few decades. Especially in the shipping industry, which is a major contributor to the CO2 emission, we're looking to replace it by ammonia. Green ammonia can be produced from renewable power and using hydrogen to ensure that we are able to meet the net zero demands. But there are major safety issues that needs to be dealt with, especially comparing ammonia with hydrogen. Hydrogen is highly flammable, but ammonia is more toxic. And then in the past, we have been able to deal it with water sprays and other methods, but still, if you're looking at the scale that we are trying to go towards, it's going to be a big issue that needs to be dealt and discussed before it can be implemented. The next process that we're trying to look at in terms of ensuring we are able to meet the net zero demand or decarbonization is the industrial electrification. We have seen this in the past, that some of the process equipment being electrified, but we're looking at a scale where we are trying to ensure that the whole process industry is electrified to make sure that we are able to bring down the carbon emissions. But with that, we are also looking at the hazards that the new workers have to deal with in terms of changing technology. Right now, we're looking at seeing how we can be changing the process from electrifying the heating process, the cooling and the compression, but also to stimulate the reaction, the chemical reaction using plasma or existing electrochemical processes that need to be modernized. In another aspect, we are looking at using process intensification and electrification as a two-pronged effort to minimize the impact of CO2 emission, and that drives the new processes. The electrification with the process intensification is expected to change the chemical processes such as catalyst by plasma technology, electron magneto, hydrodynamics, microwave, UV radiation, laser light, ultrasound, shock propulsion, and enhanced gravity. These electricity stimulators, they generate ions and radicals and make use of ions to push those for flow by magnetically directing and forcing charged particles, or generate locally forced high energy temperature spots, providing activation. So this is one of the processes that we are trying to see how we can change the chemical process to modernize it and make it electrical so that we're not cutting down on the emissions. If we look at it, some of the major industries that are really contributing to the CO2 impact is the steel production and the cement, which play a major part. Currently, we're looking at around 4,000 metric tons of CO2 emission from some of these major chemical processing plants. So if we want to change that, in the next 20-30 years, by 2050 at least, we're looking at changing the whole fossil fuel processing to charge them using electricity. So in the diagram, if you see, the orange line indicates the one that are currently fueled by fossil fuels that being changed to electricity. That will bring down the CO2 emission by 80 metric tons, which is multifold reduction in the CO2 emission if we had to just electrify some of these major chemical industries. We are looking at changing the chemical processes using electrification. So if we look at it, then so some of the processes using the intensified separations, plasma technology, microwave and ultrasound and electric are going to change the way we even process chemicals. So that will enable us to produce large volume of chemicals and fuels, some of the specialty chemicals and pharma supply chains, and then the large volume chemicals and fuels. So this is some of the processes, the electrocatalysis, conversion, electrolysis, and the heating, upgrading, and electrocatalytic conversions are essentially going to aid in terms of playing a major factor in the electrochemical processes or the chemical processes. So with this, again, we open a new set of safety hazards that need to be addressed. If we are trying to electrify the whole process industry, then we're looking at unprecedented demand for high voltages and high currents. The current working environment are not trained enough to handle this large demands for voltage and currents. If any mishap due to lack of technical physical understanding may create new complexities that need to be trained. Again, process control issues, conventional process control training has not come to address these things. The process hazards by heterogeneity in upscaling the whole process. Say, for example, peroxide formation in case of naphtha cracking, the exposure to fast pulsating fields, and then the stress on the whole grid in terms of electrifying the process industry is going to create new blackouts or common power failures, and then the whole idea of shutdown safely. With this, we're looking at hydrogen and ammonia taking over as the new technologies of fuel for the common man. So that popularization is also going to create or ask for new questions in terms of safety. As we all know, or we've seen these past presentations, how the highly flammable hydrogen and its burning velocity, when it comes into high dense areas like New Delhi or other places like Mexico City or Tokyo, we have to be planning to ensure that we are able to meet or safely handle these things. The industry has standards and material competency available, but still it is an evolving process and needs to be addressed if we're going to be proactive in terms of getting over to hydrogen. Again, the big question is, if it becomes popular as the next fuel to power our cars, the safety in terms of dispensing it in high living or high dense living quarters or fuel electricity today. We have seen the natural gas explosions in high dense areas. We have seen the catastrophe, but hydrogen is expected to be more deadlier than that. And what how we going to manage that is something that we need to deal with right now, rather than something that happens in the future in terms of an accident. So batteries, soon most of the cars are going to be running on batteries. So the large number of battery cells per string in a grid scale energy storage results in high voltage levels and creates risk for workers who are not qualified to handle this. Arc flash blast, again, high string voltage affects the shock and arc flash blast potential that increases the risk of injuries. The fire is something that we are still learning how to handle lithium-ion battery fires. This is something that is commonly seen in the news as how the fire protection agencies are not able to manage, and there's no safety protocol to see how we can put out the fires. So these fires that are caused by dendrites or thermal runaway cannot be put out with conventional fire retardants. So this needs to be addressed as well if we're going to be going into the scales that we have not seen so far. Any burning material from this is if we are going to scales that we have not seen before, the toxicity of it, the electrolytes that are used in some of the flow batteries can be toxic to the environment and human population. So incidentally, generate smoke from battery fires that can be toxic, which we have not studied very much about. So the electrolyzers, in the previous presentations, we have seen that any membrane permeation results could be contributing to the mixture of hydrogen and oxygen that could make it more catastrophic. And then the fuel cell membrane degradation and perforation, that needs to be addressed to ensure that we are able to mitigate any safety hazards resulting from it. Wind generator, those are mainly the strong vibration and fatigue failures, the accidents that are carried out or happening because of the transportation of these heavy equipment, and at harsh conditions, what happens to these maintenance of the generators. So these are some, again, other issues that need to be dealt with in terms of ensuring that we are moving safely towards the new energy demand. The material hazards is one thing that is largely not discussed as we actually enthusiastically look at the energy, new energy. The toxicity of the uncommon compounds, dusts, and gases that are going to be produced from use of new chemicals, the flammability of these new materials or the existing ones that produce fine grains. So how do we recycle the lithium-ion batteries that are going to be coming out largely and in the scales that are unprecedented in terms of matching the cars that are going to be coming out in the future? So we've seen a lot array of different aspects of the whole energy transition. With that, we want to have some of the questions that needs to be addressed as the world changes and the conditions are changing. Know-how grows, new capabilities arise. So with these new capabilities, we need to understand the challenges that we face by bringing the new hazards and new risks that are not really understood at this point. So this is with the new materials and new process types, the latter mostly to cut back on carbon emission. The large scale operation of or the large scale of operations and human factors are what makes the risk serious, because up to now we have seen scales that we are able to manage, but then as with doubles and quadruples, how are we going to manage this is a big question. The hazard identification and imagining scenarios are the notoriously weak elements in this risk assessments. There is some progress over the years, but too slow. Only after before an accident happens, and I think we need to address it right now before we go about understanding how to manage this once a serious accident happens. And I think that is a big question that needs to be answered before we progress into the new energy transition. So that brings us to the end of this presentation. And if there's any questions, we'll be happy to answer that.
Thank you, Hans, and thank you, Edison, from this wide and holistic presentation on the industry safety challenges in the energy transition. So we have room now for a final round of questions or comments, both from delegates and from the authors of the previous speech.
Yeah. Let me just comment that the popularization of hazards is the same. Well, it's only a very short term, but it is the same that Dr. Cozzani mentioned in his one of his last slides. Of course, that really I see as a problem. How to get the sufficiently competent technical people, because well, you know how it is. If you have a heating facility in your house, who is going to maintain it if something happens? And well, you have to have quite a good competence if to deal with hydrogen or with the other heat pump hybrid with hydrogen or whatever.
Yes, you're right, and the same consideration applies also to the management of batteries as and of accident, for example, also car accidents and emergency actions, which are not fully understood in the correct line. And so, any other comment? Do we have brave and curious people from the public for a comment? If not, we are just in time, and I'm very happy to see that we have a good attendance till the end of the webinar. And I wish to thank all the keynote speakers for sure, all providing us food for thought, and all the virtual delegates, especially those that attended until the end of the webinar. The webinar addressed some of the main issues of energy transition and identify main bottlenecks to go towards a safe and sustainable energy of the future. And I am convinced that as chemical engineers, we can all make the difference, and we should do it. With this message, now I close our workshop, thanking again you all very much indeed for attending, all the speakers for their contribution, and a special thank to the European Federation of Chemical Engineering for the organization and support. I remind that the registration of the presentation will be available on the EFCE website. So, goodbye to all.
Thank you very much.
Thank you, Peter, and thank you all.